Hello, good evening. I hope I am audible. Okay, so let's start today's discussion. First, I shall share my screen. Okay, so welcome to the online tutorial session of Power Electronics Applications in Power Systems, week 11. Yeah, so in this week, we will discuss about the power electronic converter based compensators. Till now, the compensators we have discussed are shunt compensators and series compensators. Uh, for example, SBC was a shunt compensator, static work compensator, and TCSC, thyristor controlled series capacitor, it was a series compensator, right? The basic idea was to control the susceptance in case of shunt compensator and uh, to control the reactance in case of series compensator. So by offering a variable susceptance or a variable reactance, we usually control the amount of reactive power that needs to be injected or that needs to be absorbed from the system, right? But the power electronic converter based compensators, their operating principle is a bit different from the previous compensators, right? How do they operate and whether they are more advantageous than the previous ones or they are not very practical, that we will discuss today. What are their advantages or their disadvantages, all these things, right? This is a broad classification of power electronics based compensators. So as we already discussed, there are two different categories, shunt compensators and series compensators, right? And under shunt compensators, we have several other subdivisions, right? Control susceptance based compensators. That's what we have discussed so far. Yeah, can you please unmute yourself? Thank you. You are able to see the screen, right? So we were discussing that the division, the different categories of power electronic based compensators. This control susceptance based compensators, this we have already discussed in detail. Uh, so TCR, TSC, FCTCR, MSCTCR, TSCTCR, all these things come under controlled susceptance based compensators. TCR we know, thyristor controlled reactor. TSC also we know, thyristor switched capacitor. Then FCTCR, that is fixed capacitor thyristor controlled reactor. MSCTCR, that is mechanically switched capacitor, then thyristor controlled reactor. So all these things have been discussed in detail. And then there comes converter based compensators, under which we will study that is called STATCOM. That's static static compensator. Okay, static synchronous compensator. This is a shunt compensator. And again, there are series compensators. Okay. So there are series compensators, and the subdivisions are control impedance or reactance compensators that we already discussed in the last few online sessions. That TCSC, that is thyristor controlled series capacitor, TSSC, thyristor switched series capacitor, and GCSC, GTO controlled series capacitor. Right. We mainly discussed about TCSC, thyristor controlled series capacitor, its applications, its operating principle, the control characteristic, all these things. And here also there is a converter based compensator, that is triple SC. Okay, that is triple SC. This we will also discuss. Okay, but first the topic of discussion will be STATCOM. The converter based compensators can be divided like this. So based on application, the first one is power transmission system. So STATCOM, then triple SC, UPFC, these are power transmission systems. Excuse me. Whereas there are certain power electronic converter based compensators which are used in power distribution systems like DSTATCOM, DVR, and UPQC. Okay. So these are used in transmission systems and these are used in distribution systems. Yeah. So this is the single line diagram of a STATCOM, right? So obviously this is the bus. This is the bus. Then there is a step down transformer. So this part we already saw in case of SVC, right? So there was this is a three-phase system, but uh, as this is a single line diagram, it has been represented by these three lines. This is the step down transformer whose leakage inductance is X sigma. And then there is VSC. What is VSC? VSC is voltage source converter. Okay. VSC is called, the full form of VSC is voltage source converter. This is a power electronic converter. That means the components of this converter are made of power electronic devices. Like here you can see the thyristors, right? So VSC can be designed using thyristors or using IGBT or using MOSFET also. Here it has been shown by thyristors. Okay. So these are thyristors and these are diodes. So we just write voltage source converter. Source converter. And this is the simplified equivalent symbol. So STATCOM is symbolized by this, a controlled current source. Okay, controlled current source like this. Suppose this is the system voltage V angle 0, and here there is the STATCOM. Okay, and this is the reactance of the step down transformer, right? Actually, the idea is here there is the system voltage, suppose V angle 0. Okay, V angle 0. And here in this side, the STATCOM produces a three-phase voltage, suppose that is VC, that is VC angle 0. Okay. VC angle 0. The the main function of a STATCOM is to provide reactive power compensation. Okay, so based on this output voltage of the STATCOM, it is decided whether it will inject reactive power or it will absorb reactive power. That is decided by the magnitude of this VC, the voltage produced at the output of the VSC. Okay. So yeah, so this is the line, transmission line. We know what will be the active power. The active power is VC dash by X sigma sine alpha. What is VC dash? This VC dash is the voltage equivalent at the bus side of the transformer. So we have just this is the converted voltage at the bus side. So at this side, after the transformer, if the voltage at this side is VC, the voltage at this side is VC dash. Okay, VC dash. So this is the active power. And what is the reactive power? The reactive power is V times VC dash minus V by X sigma. Okay. Actually, this is if, as I told that this STATCOM is used for reactive power compensation. So usually the phase angle of V and VC dash, that is 0. That is alpha is equal to 0. There is no phase difference between V and VC dash. So this P is equal to 0. There is no active power injection, only reactive power is there. So when alpha is equal to 0, Q is, the value of Q is this. This value is at alpha equal to 0. Okay. Alpha equal to 0 degree. Fine. So alpha equal to 0, the reactive power is non-zero, but the active power is 0, obviously. Right. So, and you can understand that if VC dash changes, if this value changes, then Q will also change. So the controlling parameter here is VC dash, because V is constant usually and X sigma is also constant. Yeah, so here two cases have been shown. The first one is when VC dash is greater than V. The output voltage of STATCOM is greater than the bus voltage. Okay. In that case, what happens? So this is VC dash and this black phasor, this one is V. And if we just apply KVL, then what happens? Then what is the equation? The equation is V is equal to VC dash plus J I X sigma, right? Where I is the current injected from the STATCOM. Okay. Now, if VC dash is greater than V, then obviously the direction of I will be J I sigma will be like this. Okay, because V is the summation of VC dash and I X sigma, J I X sigma. So this vector will be like this, and therefore I will be 90 degree leading the bus voltage. I is 90-degree leading. That's why this is the capacitive mode of operation. And the second case is inductive mode of operation where Vc dash is less than V. Vc dash is Vc dash is less than V. So in that case, if this is Vc dash, then it will get added with Ji x sigma, and this total is V, the bus voltage. That's why here the current I is lagging the bus voltage equilibrium. So that's why this is the inductive operation. Another important aspect is the control characteristic. Here, the control characteristic of STATCOM is presented here, and the control characteristic of SVC is this. So there is a difference. What is the difference? The difference is that the control that we already learned that control characteristic can be horizontal to the x-axis, or there may be a slightly positive slope, a very slight positive slope in the control characteristic. By implementing this, we get certain advantages, right? By having a slightly positive slope. Here, if you see that, so even if the system voltage changes, there is no, there is, we don't have the same amount of compensation here. Okay. If the system voltage is this much, then also we can have this much compensation. If the system further declines, here also we can have this much compensation. But in case of SVC, this amount compensation changes with the voltage. As the voltage reduces, the compensation also reduces, right? In this voltage, the compensation is this. As the voltage increases, the compensation also increases, right? This is one advantage, that irrespective of the system voltage, the amount of compensation is what stack off. Okay, now we will solve the numericals or the questions that we have. Before that, do you have any question? Okay. First question is, which of the following is not an application of STAT? So the first option is reactive power compensation, both capacitive as well as inductive mode of operation. This is obviously an application. Voltage controlling power systems. This is also an application because STATCOM is used to control the system voltage, right? The third option is backup power demand during high load demand and grid outages. And the fourth option is enhancement in transient stability. So the applications of all those applications uh, are for STATCOM also. It can also enhance the transient stability. It can also control the system voltage, and obviously it can provide reactive power compensation. So this one is not application of STATCOM. backup power demand during high load demand and grid outages. This is not an application of STATCOM. Okay. The indicator capacity mode of STATCOM is that whether the STATCOM is operating in inductive mode or it is operating in capacitive mode, that depends on the magnitude of DC dash. What is DC dash? DC dash is the output voltage of the STATCOM, that is to the up side, because there is a down transformer. So basically it depends on the output voltage of the STATCOM, magnitude of the output voltage. So yeah, option B, controlling the output voltage. This is the correct option. Third question. Compared to SVC, the STATCOM offers. First option is higher efficiency and faster response time, then lower cost and easier installation, easier control mechanism, more limited operational range. The advantage of STATCOM over SVC is that it has higher efficiency and faster response time. The STATCOM is faster compared to SVC and it has higher efficiency. Okay. The fourth question. Which of the following compensators are used in distribution systems? Triple SC and UPQC, DVR and UPFC, DVR and UPQC, STATCOM and UPFC. For distribution system, DVR and UPQC are used. Okay. DVR and UPQC. If I am not wrong, the full form of DVR is distribution voltage regulation regulator, and UPQC is power quality conditioner, something like this. Okay, you can verify it from the lecture video. Okay, but these two are used in the distribution system. Next question. Which of the following compensators are used in transmission system? So STATCOM and UPFC, these two are used in the transmission system. You can refer to this table. You can refer to this table. Okay. STATCOM, Triple SC and UPFC, they are for transmission system. And these STATCOM, DVR and UPQC, they are for distribution system. Okay, question number 6. The interfacing step-down transformer is used in STATCOM. So what is the treatment of step-down transformer? The first option is PXC. Whenever you are using a power electric converter, definitely there will be some harmonics. But those harmonics can be handled, okay, by proper modulation, and there may be some requirement of filters. But the requirement of transformer is not to eliminate the harmonics, okay. STATCOM under fault, this is also not true. To enable operation in inductive mode, to reduce the rating of STATCOM. This is the correct. The transformer steps down the voltage, so rating of the STATCOM reduces. Okay. Next question. Which of the following is correct about STATCOM in terms of transient stability enhancement? The stability margin increases, the stability margin decreases, for same rating of SBC and STATCOM, the range of STATCOM is more. For same rating of SBC and STATCOM, the range of STATCOM is equal. The correct option is the stability margin increases when STATCOM is used. Okay, the transient stability margin increases. Question number 8. At the correct statement among the following. The STATCOM has faster response than SVC, but STATCOM has poorer response than SVC at low voltage conditions. The reactive compensation that STATCOM provides is dependent on system voltage. The STATCOM operates in capacitive mode if the magnitude of output voltage is lower than the system or bus voltage. The STATCOM operates in capacitive mode if the magnitude of output voltage is higher than the system or bus voltage. Option D is definitely correct because when the output voltage of STATCOM is higher than the bus voltage, then it operates in capacitive mode. Other than that, the first option, it has faster response than SVC, but STATCOM response than SVC at lower voltage condition. That is not true because in the control characteristic we saw that STATCOM can provide the same amount of compensation irrespective of the system voltage. But the compensation of SVC varies based on the system voltage. As the system voltage reduces, the compensation also reduces. The reactive compensation that STATCOM provides is dependent on system voltage. No, that is not true. It is independent of the system voltage. That is evident from the control characteristic. The STATCOM operates in capacitive mode if the magnitude of output voltage is lower than the system or bus voltage. That is not true. Option D is the correct option. Okay. Okay. The next question. The STATCOM can be used for power system oscillation damping by varying the frequency of the output voltage of the STATCOM, varying the magnitude of the output voltage of the STATCOM, injecting active power into the system, varying the susceptance of the STATCOM. So STATCOM doesn't operate in that way. That that is applicable to SVC, where the susceptance is varied. So this is not correct. This is not correct. Then injecting active power into the system is also not correct because STATCOM is used for reactive power injection or reactive power absorption. Then varying the magnitude of the output voltage of STATCOM, this is correct because if you see the closed loop control, there the voltage of the output voltage of the STATCOM is varied to damp the system oscillation. Okay, so option B is correct. Actually, in power system, in basic power system, if you see the frequency, and the active power, they are correlated. So if your active power changes, the frequency changes, and the voltage, the system voltage, and the reactive power, they are correlated. If the voltage varies, Q varies. Okay, so this is a pair and this is a pair. Okay. Okay, so this is the numerical problem. Till this point, do you have any question? Okay. If you do not have any question, I shall take a 10-minute break and then I shall solve the discount problem. let's start the numeric. Transmission system is STATCOM at 220 kV bus. The STATCOM is connected to different transformer releasing the STATCOM injects 400 5 per unit side of the transformer. Consider the bus voltage response at 1 per unit. Define the output now this question. What is Q? Yeah. Now, initially, the STATCOM was in 200 kVA. Right. When the output voltage was C dash was 1.05 kV. Afterwards, the STATCOM 500 kilowatt. Okay, extra 100. What will be VC dash? Okay, that is the question. So we can write what is constant. So we can write like this: VC1 dash minus 3 pi x sigma is equal to 400 to 10 power 3. 10 power 3. And D in this is suppose equation 1. This is equation 1. And equation 2 is V into V2 dash V2 minus V x sigma equal to V2. This is equation. Okay, fine. So we have two conditions. The amount of reactive power. Now, if you just do 2 divided by 1, because we don't know the value, so what we will get VC1 2 divided by VC2 dash VC2 dash minus VC1 dash VC1 dash minus 5/4, right? 5/4. Excuse me. We 1 per unit that is given. So, and what is the actual value? Value is 220 kV. Bus voltage. So, we write like this. So, we can just multiply 220 in the numerator and denominator. We will cancel out the others. 2 PC2 dash minus 1 I think 400 kilo and PC, PC dash was right. This is 1.05 minus 1 is equal to 5/5. Now we solve this. BC dash. BC2 dash is 2 1.0625. 1 point. This is in per unit. Okay. 1.0625. Okay. This is VC2 dash. If you multiply this with 220, then you will get the actual value. And that comes out to be 233.75. Option B. Okay. This is per unit. Per unit. Okay. Okay. The next question. If the react, yeah, is it okay? Is it okay or you have any question? If the reactance of the step down transformer is zero point 0.1 per unit, determine the per unit current injected from the STATCOM into the system corresponding to a reactive power injection of 500 kVAR. So here the value of X sigma is provided. X sigma is 0.1 per unit. 0.1 per unit. Okay. 0.1 per unit. Corresponding to a reactive power injection of 500 kVAR, what is the current? So we already know how to find out the current. The current injected by the STATCOM is equal to PC dash minus V by X sigma. Okay. Here VC dash is actually greater than V. Okay. So that's why I have written VC dash minus V by X sigma. What is VC dash in per unit? That we already found out 1.0625. So 1.0625 minus 1 because the bus voltage is 1 per unit and it is constant divided by 0.1. Okay, 0.1. So what is the value then? The value is 0.625 per unit. 625 per unit. Okay. Excuse me. So the correct option is option C. Okay. Okay. So do you have any question?
No, ma'am.
Can you say a little louder? You are not audible.
No, ma'am.
Oh, uh, okay, you understood, right? The numerical problems.
Yes, ma'am.
Okay. So I think in this week's lecture there were not much in terms of numericals. Mostly there were theoretical questions. Okay, so then thank you for attending. We will meet in the next week. Okay.
And
Thank you.